Welcome everyone to lesson 3.15, which is rates of change in polar functions. It's our last lesson together in pre-calculus. Kind of bittersweet, both happy and sad. Let's get started. So in this lesson, we are not only talking about polar functions, we're going to talk about some aspects and some behavior in a little bit more detail than we did in the last lesson. So for our first question here, we are given r is equal to 6 sine 3 theta. We know that to be a rose curve. And we want to describe whether the r value, the output, is increasing or decreasing, and positive or negative on these intervals. Now, we talked about a little bit last class that it's hard to determine whether r is positive or negative or increasing or decreasing if we just look at the polar graph. So that's where having the rectangular version helps out a little bit. So we're going to really use the rectangular version for this style of question. So if you have multiple different colors, get those ready because we're going to analyze this function as best as we can. For this one, we're going to look at the interval from 0 to pi over 6, which is starting at the pole and going to the tip of the first petal. We can see that graphically here. Let me try to do that as best we can here. So it is this part here. Get your colors ready for this because we're going to color code them. Then the second one we can do in green. There we go. So green. So that would be tip of the first petal back to the pole. The next one is going from the pole to the tip of the second petal. And then we are returning back from the petal to the pole, back from the petal to the pole. So if I want to color code this, it would look like this, then this, then this, then this. So that's what essentially is going on there. Fun. Super, super fun. So let's actually analyze whether they're positive, increasing, negative, decreasing, so on and so forth. So for the first interval, the blue interval, it is clearly positive and going up, so it's increasing. So this is positive and increasing. And we can see it's going away from the pole. That's important for later. The green, we are positive but decreasing. So positive, decreasing, we are going towards the pole. Also interesting. The red is negative and decreasing, so negative. That's awful. And decreasing. And we can see that the red is going away from the pole. And the white is negative and increasing, so negative and increasing. And we can see it's going towards the pole. So we talk about r's behavior. To determine the polar function's distance from the pole and how that's changing, we have to look at r and its sign, which we kind of alluded to here. Positive increasing was going away. Positive decreasing going towards. Negative decreasing going away. Negative increasing going towards. So if r and its rate of change have the same sign, it's moving away from the pole. Negative and decreasing are both negative. And if they have opposite signs, it's moving towards the pole. Here's a little chart to help you with that. If you want, you can pause the video and copy that down. I'm moving on because it's relatively simple. And foreshadowing, this is very similar to speeding up and slowing down in calculus. I know that might not resonate with you now, but maybe this will ring some alarm bells when you get to speeding up and slowing down in calculus, because students tend to struggle with that a little bit. Same kind of thing. Same sign, moving away. Opposite signs moving towards. So let r equal f of theta. We're going to describe the function's behavior from 0 to pi over 2. So from 0 to pi over 2, we can see that r is positive. So r is positive. And it's also going from 0 to 5. It's increasing. So r is increasing. Those are both positive, right? So that means that the function is moving away from the pole. Makes sense. Both positive, increasing, both positive, the function's moving away. What about from pi over 2 to pi? Well, we can see that r is positive. All the numbers are positive, but we're going down. We're decreasing. So r is decreasing. What does that mean? Well, it means that the function is moving toward the pole. Not bad, right? Relatively simple so far. Rate of change. Ooh, how do we do rate of change? Well, it's the difference in the output over the difference of the input, right? So same idea, except that r is your output. So for rate of change for polar functions, it's r2 minus r1 over theta 2 minus theta 1. Same kind of thing we've been doing, right? I know that the difference is pi over 6 anyway, so I'm going to go ahead and put pi over 6 as my denominator because I know that's the difference. Pi over 3 is 4.33, and then pi over 6 is 2.5, so we can figure this out. Oh, my calculator's frozen. Perfect. All right, so we're going to do 4.33, take away 2.5, and we get 1.83. Then we're going to divide this by pi over 6. So we're going to divide this by pi over 6. And we get about 3.495. So the rate of change between those two values, between those 2 points, is about 3.495. When we think of rate of change, we're really thinking in a rectangular frame of mind. We're not really thinking about a polar frame of mind. Just keeping that in mind, we're looking more at if we switch the thetas and the r's to x's and y's. If we want to estimate a value, that's where this average rate of change is important. If the average rate of change, the interval we used, contains this value, we can actually use the average rate of change to predict values, and we do that by using lines. Remember that lines are y, well, not y2, is y minus y1 is equal to m times x minus x1. This is one version called point slope form. It's my favorite. We've talked about it before, but it might have been a while. Just keep that in the back of your mind. If you have to estimate a value, you're going to use a line to do it. We're going to say that this is our m, and then we just need to pick a point, and you always want to pick whichever one's easiest. If I look between these 2 points, which one's easier? This one is definitely easier. So for my line, I'm going to do y take away the r, so that's 2.5, is equal to the slope, which is 3.495 times x take away the angle, which is pi over 6. Great. That's the line. How do we predict the value? Well, we just make this the x. We substitute this in for the x, and then we solve. So if I want to do it all in one go, I would do y is equal to 3.495 times, and the value we're substituting is pi over 4, take away pi over 6, plus the 2.5. If you're not sure whether it's a plus 2.5, by all means ask. But it's plus 2.5. Let's actually plug this in the calculator and see what's going on. All right, so we're going to do 3.495. Oh, I missed the 3. 3.495 times pi over 4, take away pi over 6, plus 2.5. And that gives us an estimation. So the estimated value, f of pi over 4, is about 3.495. 4, 1, 5. And we can see that we don't really know what it is, so that's going to be our best prediction. But we might be asked to interpret that result later. Pretty good. Hopefully we're feeling good now. Let's get started. So first thing I'm going to do is I'm going to plug this into my y equals screen. Got to make sure I'm in polar mode. So my y equals screen, 3 plus 5 sine theta. That is not what I want. Sine theta. There we go. So this is a limison. Let's actually figure out what's going on here. So we want a table. So I want to go to table set, and I want my independent to be ask. Let's go to the table. Perfect. So these are our values. What intervals is f? Increasing. Well, increasing means that our outputs are going up, and that happens from here to here. So that would be 3 pi over 2 to 2 pi. Where are we decreasing? Well, pi to 3 pi over 2. Are we guaranteed an extrema? So are we guaranteed an extrema? Well, we go from decreasing down to increasing up. It kind of works either way. I know it's mirrored. We are guaranteed a minimum here. So yes, because the function switches from increasing to decreasing. And if we want to be more specific, we can say that we are guaranteed a relative min. Here we go. Is the distance between the function and the pole increasing or decreasing from 5 pi over 4 to 3 pi over 2? So in here, are we going further away, or are we going closer to the pole? Well, I know that r in this case is negative, and we can see that it is decreasing. So if r is negative and decreasing, that distance must be increasing. The distance between the pole and the function is increasing because r is negative and decreasing. There you go. So if you say something, make sure you back it up, right? Is the distance between the function and the pole increasing and decreasing between pi and 7 pi over 6? So pi and 7 pi over 6 is here and here. R is positive and r is decreasing. So let's write that down. R is positive. That's not how you spell positive. R is positive and decreasing. So if r is positive and decreasing, that means that distance is decreasing. We're going towards the pole, right? So the distance between the pole and the function is decreasing because r is positive and decreasing. Fair enough. Let's find the average rate of change. Whew. Okay, so I don't know what those values are off the top of my head. I don't want to keep writing them down. So we have 3 pi over 2 and 7 pi over 4. 3 pi over 2 is negative 2, so I'm just going to type in negative 2 to store that in my calculator. And then negative 0.536 are the values I want. So find the average rate of change between them. I know that there's pi over 4 difference, so It's going to have a denominator of pi over 4. And we're going to take the new one and take away the old one. So negative 0.536, take away negative 2. Don't know why the computer is trying to do that. So we can do this all in one step. Alpha y equals enter. Negative 0.536 minus negative 2 all over pi over 4, and we get about 1.864. Very cool. On what intervals must the function have zeros? Well, we have zeros when we switch from negative to positive. So we're going to have a 0 between these two and a 0 between these two. So we're going to have 1 between 7 pi over 6 and, 5 pi over 4. 7 pi over 6 and 5 pi over 4, yep. And then 7 pi over 4 and 11 pi over 6. 7 pi over 4 and 11 pi over 6. Again, because they switch from negative to positive, so if you needed a reason or justification, that would be your justification. We switched the sign of the output. So compare the estimated value of 5 pi over 3 to its actual value. So 5 pi over 3 is in this interval, so we're going to use our estimation the same we did before. We're going to call this m. So we're going to have y is equal to 1.864, and then we're going to have 5 pi over 3 take away. Which one's nicer? I'm assuming the one with negative 2 is nicer. Which one has negative 2? That would be 3 pi over 2. So take away 3 pi over 2. And then we're going to add 2 to it because we would take 2 away on the other side. If we plug this whole thing in our calculator, we should get an estimated value. So 1.864 parentheses. And then I'm just going to use this tool here just so we don't mess anything up. 5 pi over 3. Take away 3 pi over 2 plus 2. And we get an estimated value, so we get f of 5 pi over 3 is about 2.976. How does that compare? That's negative 1.33. So f of 5 pi over 3 is equal to negative 1.33. So how does it compare? This is oh, I see what I did wrong. Okay. What I did wrong is this should be a minus. There we go. So I was wrong. Let's fix that. So f of 5 pi over 3 is equal to negative 1.024. It's actually equal to negative 1.33. The actual value is lower, right? So this is an overestimate. So it is an overestimate. And if you need to explain why it's an overestimate, it's because the predicted value is greater than the actual value. That is it for us. It has been a fun ride. If you have any questions, let me know. Otherwise, I hope to see you in calculus.